Hey all you cool cats and kittens, we are back for another AP Physics 1 discussion seminar, and today we are reviewing projectile motions, everyone's favorite two-dimensional kind of motion. So projectile motion concerns ourselves with motion of projectiles. What is a projectile? A projectile is an object that is only under the force of gravity. So no air resistance, no lift, no thrust, no other forces other than gravity. So if we were to draw a free body diagram for a projectile, we'd have our little dot at the center, and we'd have only a single force acting downward. This is our force due to gravity, and that's what a projectile looks like. As long as it's basically in the air with nothing else going on it, it is not a projectile. Now you're right that in reality nothing is a true projectile because there's always some small amount of air resistance acting on the object. However, in most cases it's going to be small enough that we can safely ignore it and get basically the same answer. So we're going to ignore air resistance and any other force you could imagine other than gravity. So because gravity is the only force acting on the object, the acceleration of the object is g, and it is downward. On Earth, g is of course 9.81 meters per second squared, or on the AP exam you can round this up to 10 and make your life a lot easier due to the easiness of working with a 10. So this is our acceleration. It is downward only in the y direction, say. So we know what a projectile is. Projectile, when it's moving, the problem is usually going to be framed as the object is launched with an initial velocity, vi, at some angle above the horizontal, theta. And based off this prompt, this is all you're going to get. The object's launched at this speed, at this angle. We can ask ourselves, how far does it go? How high does it reach? How long will it take to hit the ground? So there's all that good stuff going on just from this simple issue, or simple setup. The trick is this vector points in both the x and y directions. And so we need to keep track of what's going on in each of those directions separately. So we're going to separate what's going on in the x from what's going on in the y. And essentially what we're going to do is each direction is going to get its own set of variables. There's going to be an acceleration for the y. There's going to be an initial velocity for the y. There's going to be a displacement in the y. And the same thing is true for the x direction. So we're going to get a, set of x equations and a set of y equations. Well, let's set up our y equations. What's new here is now the object's able to go up in the air, so that might be the more special direction. So our kinematics say that we have y as a function of time, y final is equal to some initial y, and again, y refers to the height, the vertical position of the object, plus some initial velocity specifically in the y direction times t, and then our acceleration is g downwards. I'm going to go ahead and foreshadow a negative sign here, 1/2 gt squared. And our other kinematic equations get variance as well. We're all looking at specifically what's happening in the y. And our third and final, that should be y initial y. V final y equals v initial y minus gt. So there's our y set of equations. They're exactly the same as our other kinematic equations for one dimension, but we've sort of specified that we're only looking at the up and down direction, and we're using the acceleration is specifically the acceleration due to gravity. The acceleration in the x direction is 0. If gravity is the only force in this object and it's downward, there's no other forces acting on it left and right once this thing is in the air. So our x equations work out to be a lot simpler. We have some initial x position plus some initial x velocity times time. The acceleration in the x direction is 0, and so this whole messy quadratic term drops out. Our second equations basically just tell us, because a is 0, that the initial velocity in the x is the same as the final velocity in x, and therefore v is a constant. Vx is a constant. Does not change. If you know the x velocity at the beginning, you know it at the end. If you know it at the beginning, you also know it halfway through, a quarter of a second through, pi seconds through, whatever. You know the x velocity everywhere, and that's really powerful to have at your disposal. So these are our equations for projectile motion. They're exactly the same as the regular kinematic equations, but we've adapted them to a specific situation. Now let's take our example. Let's say we have a 10 meter per second at 30 degrees. So we've kicked a soccer ball at 10 meters per second at 30 degrees above the horizontal. And we want to know the time of flight. So how long was it in the air before it landed again? We want to know the maximum distance covered. And we want to know how high it got, maximum height. So the time of flight, we want to know how long it's going to be in the air. We want to find the time it takes to land back down on the ground. If we're on level ground, I'd hope that most soccer fields would be level, that the initial height, so level ground, if we start and end at the same position, this tells us that the initial height is equal to the final height. And if we're setting our initial height as a reference point, these could both essentially equal 0. So we're going to take our first kinematic equation. We're going to set both of the positions to be 0. So 0 equals VIYT minus 1/2 GT squared. If we want to get the initial y velocity, well, we're given the initial velocity, but that's the initial velocity as a whole. We have to break it down into its components. So if I want the y, that's the vertical side of this triangle, VIY. The horizontal side of the triangle is VIX. VIY is the opposite to our angle here, so we're looking at 10 sine of the angle. Here our angle's 30 degrees. So that's going to be equal to 5 meters per second. And VIX is going to be 10 cosine 30 degrees, which is going to be 10 root 3 over 2 meters per second, of course. All right, so now that we know that VIY is 5, we can plug that into our formula here. We get 5t minus 1/2. We'll substitute g in as 10, t squared. I have a t on each of my non-zero terms, so I can cancel out a factor of t on each one. So my equation simplifies to, I'm going to go ahead and move this negative term over to the other side. So we get 5t equals 5, and therefore the ball is going to hit the ground after 1 second. So our time of flight is 1 second. Now I want to find the maximum distance. The maximum distance occurs when the ball has essentially completed its whole time of flight. So it's going to reach its maximum distance in the x direction when we plug in the time of flight into t here. So t is 1 second. We're just going to plug that in. X final is equal to, we can always usually set our x initial equal to 0 as a reference point. We're going to get 10 root 3 over 2 times 1 second 5 times root 3 is like 5 times 1.7. It's 8-ish. I'll leave it in root form so I don't have to embarrass myself with guessing what the decimal place is. So it's not meters per second, it's meters because it's a distance. So we now know how far it goes. So we found the maximum distance, and we can also figure out how high the ball will go. Instead of looking at xf, we can look at the y. We want to figure out how high it goes at its maximum height. So the trajectory of a projectile. What comes up must go down, so it goes up in a parabolic arc and eventually falls back down to the ground. Because it is a parabola, this graph is completely symmetric. So whatever happens on the left going up is essentially the same as the right going down. So for example, if I take a little slice of this graph, one point going up, I look at sort of the mirror image going down, the velocities have sort of switched vertical orientation. So on the left, I have VYI is equal to negative VIY. It's the same value, 3 and negative 3. I'm making up numbers, but it's the same value on either side of this central point. It also takes the same amount of time to climb to the top as it does to fall back on the bottom. So T1/2 is equal to T1/2 over here. This x distance, 1/2, is equal to the half x distance over here. And this is nice and completely symmetric. So there's a lot of free information we can get knowing about the left is exactly sort of the mirror image on the right. So we know half the distance going up is the same as the distance forward it moves going down. It's the same amount of time on either side, and the velocity is the same magnitude. It just has its vertical component flipped. But from this, we can see if we know the time of flight, 1 second, this tells us it takes only a half second to get to the top. So we can use that. We can now plug in t equals 1/2 to our y kinematic equation and figure out what yf we end up with, what final height the ball ends up with at that instant. So we can get yf. Initial height is 0. Our initial velocity we said was 5. We're plugging in 1/2. We're going to minus 1/2 g is another 5. 1/2 squared is 1/4. So we get essentially 5/2 minus 5/4 equals 5/4. Yes, that's right. Meters. So it gets to about 1.25 meters in the air. There's another way we can do this that might even be faster. Remember, at the top, the velocity vector always points tangent to the trajectory curve. So at this very top, it's completely flat. The velocity points directly horizontal, and this is equal to Vix at this point. The y component is 0 at the top. So we can use that fact with our second kinematic equation, Vfy equals 0. At the top of the trajectory, this parameter becomes 0, and then we can solve for y directly with this sort of simpler equation. So we can see it, we'll get the same exact answer. Vfy is 0. We get 5 squared is 25 minus 2g is 20 delta y. When I do 25 over 20, I get exactly the 1.25 meters we got before. So there are lots of ways to do this depending on sort of which trick you use. So let's sort of summarize the tricks. let's summarize the tricks we use so that we're aware of some of the things that we can draw upon for projectile motion problems. So we have trick number 1. X and Y are connected by time. In other words, the X and Y equations we're using, they look at the same object, just different aspects of that thing. So if we're looking at, how far the ball went maximally, then that's the same as saying that happens at the same time the ball goes up and lands back at the same height it started. So in other words, like maximum distance occurs when ball returns to lowest point. So maximum distance looks at X, returns to lowest point, looks at Y. But it's important that these are happening at the same time. So once I figured out, how long it takes to return to the lowest point, that's the same time at which it's using its maximum distance. So you're generally going to solve a system of equations with t as your intermediate variable that connects them. So you're going to solve two equations together with t connecting them. The second one is we're going to exploit the symmetry. So symmetry of parabola. In other words, time to top equals time to bottom. Horizontal distance to top is equal to the horizontal distance from top back down, and that the vertical component of V flips on other side of peak. There is a caveat. Again, this really only works if you have a completely level ground. If I start and end at the same spot. If we're in a situation where maybe we're on a cliff and we're throwing a rock off the cliff, then clearly it's going to reach a maximum point and it's going to fall all the way down further from where it started to get to the bottom. It's only symmetric up to that level point. So for example, if it took 5 seconds to get up to the top, it's going to take 5 seconds to get back down to this point, and then it's going to continue falling for longer than 5 seconds to get back down. So if you have an asymmetric parabola, you can only use the symmetry argument up until the point where it crosses its original height. So like y initial is where the symmetry argument cuts off. It'll clearly take longer to fall a farther distance. So just be aware that the symmetry only works within a certain range, but it is very useful if you have that range to work with. And then the last tip is that velocity at top in y is 0, and velocity in x is constant. So if you know it somewhere, you know it everywhere. So these are our big conceptual ideas for projectile motion that are going to carry over to really helping us solve problems. The last thing I want to just talk about quickly is graphically representing projectile motion. So we have our equations as a function of time. We have x equals x initial plus v I xt, and our y equals y initial plus v I yt, yada, 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 So when we graph these functions, we have to graph, again, the position in the x separate from the position in the y. And we can see that in t, the x equation is linear, the y equation is parabolic. So our x equation is going to look something like this. It starts at some initial position, that's our y-intercept, and it's going to continue moving forward up until some maximum time where it hits the ground again. The slope of this line is the velocity, Vix. It's that constant x value. It's linear because it's maintaining this constant x all throughout its motion. So again, this is x versus t. If we're looking at y versus t, we still might have some initial height. Y initial, that's our y-intercept, and then it's going to go up and fall down to the ground. So again, this t, if this is the same object that we're graphing here, this t is going to correspond to its maximum distance, and it's going to be the same value over here when it finally lands back down on its lowest point. So we have this parabolic motion in the y, we have this linear motion in the x. We can also graph the velocity of each of these. Again, we're looking at the slope. So Vx we said is constant. Once we know that value, it's always going to have that value. So this is Vix. It's just going to be a flat line. Vy, the object moves up and then it moves back in the other direction down. So it might start going up with a positive velocity, Viy. It's going to slow down as it reaches its maximum point. The point where it crosses the t-axis is the point where it starts falling back down and going in the negative direction. So here below is falling down. This is going up. And again, the x-intercept, the t-intercept rather, is where it changes directions going from up to down. If we want to plot the acceleration, well, we kind of already know what those are. It's sort of our assumptions we make when we do projectile motion. Ax is 0. There's nothing there. It's a dead graph. Nothing there. Ax equals 0. And for ay, it's just negative g downward in the y direction. And so because acceleration is the slope of the velocity graph, the slope of this graph should be the value of g. On Earth, it'll be negative 9.81. If you're on a different planet, the slope might be different, but it still will be linear. It's not going to change just how rapidly it happens. Whew. All right, that is projectile motion in a nutshell. If you have any questions, please contact me, and have a great day.